Okay, parametric equations. Okay. Parametric equations are extremely useful tools. So the definition of a parametric equation, let x equal f of t. So in other words, f is a function of time. Let y equal g of t. Y is also a function of time. X and y are not functions of each other. They are independent functions of time. X changes with time. Y changes with time. So they do not change based upon each other. They change independently based upon time. You still have an x and y coordinate, but x does not change with y. X changes based upon its own information. Y changes on its own information. And then you have the x and y coordinate together, how they change. That's a parametric equation. One changes with time. They each individually change with respect to time, not with respect to each other. The collection of points based on some domain at some interval I, and that's supposed to be a capital I. It doesn't show up very well. It looks like a lowercase l, but that's a capital I for interval, domain, particular domain. T is limited, generally speaking. T generally does not go backwards in time. We generally don't have negative time. It's only moving forward. Once in a while, you will have a rare occasion. The collection of points x, y is defined by f of t and g of t. It's called the plane curve. The equations x equals f of t and y equals g of t, where t is an interval, are called the parametric equations of the curve. The variable t is called the parameter. So t is my parameter. T is what changes. X and y are dependent. T is my independent variable. So normally when you have x and y, one of them is dependent, one of them is independent. In this case, both x and y are dependent upon t. And you can do things three-dimensionally, and you've got x, y, and z, all of them dictated by time t. Okay? If you are in physics, you will have something we're going to be doing later on that will really help kind of solidify how this makes sense. Okay? So example 1, graph the curve defined by the parametric equations and find the rectangular equation of the curve. So I have my two parametric equations. X equals 3t squared, y equals 2t, and my interval, t goes from -2 to +2. That is my interval. I don't care for any values of t that are less than -2. I don't care for any values of t that are larger than 2. It only covers from those two things. So here's what you do. You take t, plug it in x, and what do you get? X is dependent upon t. I don't really care what's going on with y. I plug these values into x. So I take -2, I square it, and I multiply it times 3. I get 12. And I do the same thing with 1. I take 1 and I square it times 3, and I get 3. I take 0 and square it times 3, I get 0. And then, ooh, this is nice because it's a squared, it's symmetric, and I get 3 and 12. So those are the x coordinates based upon time. My x is determined by time, not by anything else but time. My y coordinates do the same thing. My y has absolutely nothing to do with x. These values I get here do not determine anything that's going on with y. Y is strictly determined by t. Y is 2t, so I take 2 times these values of t. -4, -2, 0, 2, and 4. Those are my x values, those are my y values based upon time. As time changes, x changes. As time changes, t changes, or y changes. They're independently operations. However, we combine them for the plots. So my xy coordinate is, xy coordinate, 12, -4, 3, -2, 0, 0, 3, 2, and 12, 4. And let's plot those points. Yeah, I know it's kind of hard to graph on there because the graph doesn't fit horizontally in particular, but you get the idea. However, these do not go on forever. Okay. These do not go on forever. T is limited between -2 and 2. It is not a sideways parabola going on and on forever. It has endpoints. That's why I put little dots at the end. My endpoints are 12, -4, and 12, 4. It does not go past those two coordinates. It begins at one, it ends at the other. As time begins, I start down here at 12, -4, and the point travels through here as time goes. That's the best way to think about parametric equations. As time is changing, what is my point doing? My point is determined by there. I've got a little point that travels around the graph based upon time. As time goes, it starts here, and it goes, and then it stops over here. The point is moving along that curve. As time changes, it's moving along that curve. The X and Y just gives a point. Think about your video games. What's your video screen? Your video screen is a big, giant XY coordinate, right? As time progresses, things move. They move along the X, they move along the Y, and they have that dot that moves along, driven by X and Y. It's not an equation that describes this. It's an equation that describes what's going on this way and the one that's going on that way. Think about an Etch-a-Sketch. How many of you know what an Etch-a-Sketch is? Think about an Etch-a-Sketch. One knob is the X, one knob is the Y. Time changes the knob. That point moves with time, not with X and Y. It moves with time. That's what a parametric equation is, an Etch-a-Sketch. I gotta get one of those. That'll be cool. Okay. I hadn't thought about that one before. That's let's go. Okay. Now we do have one other part to this problem. Guys, we do have one other part to this problem. We need to write it in rectangular form, which means we need to write it in terms of X and Y only without T. Sometimes you can do this, sometimes you can't. We can do this here. So I have X equals 3t squared, Y equals 2t. The idea is to solve one of those equations for t and take it and substitute it in the other. Frankly, I don't want to mess with t squared when I'm trying to solve, because that means I got to square roots, and I don't want to square root. So I rearrange this one. Divide both sides by 2. And I get t is equal to y over 2, or 1/2 y. And now I take this and put it in here. X equals 3 times y over 2 squared. X equals 3y squared over 4. And that's kind of what my graph looks like, right? Okay. The only problem with this one is I no longer have my time parameters. That graph does not have endpoints on it like the original parametric equation did. Time had parameters. I don't have parameters on the X and Y. Time is independent of what I'm doing here now. So, yeah, you can do stuff with this that you can't do with parametrics, but it doesn't really matter. Questions? Yes?
How do you decide that you think the y squared instead of the other way?
Because if I solve this one for t, what am I going to have to do? I'm going to have to square root. I don't want to square root. No square roots there. I'm lazy. That's what it made. Laziness is what made my decision, as it does for many people. Okay. So I have my two, let's say, my parametric equations. X equals a cosine t, y equals a sine t. A is a constant that I don't know. We don't call it a variable because it's not changing, but we can deal with it. T goes from negative infinity to positive infinity. That's an important thing to talk about when we get to this point. Okay. Now, it says find the rectangular equation of the curve whose parametric equations are that. when you have a situation like this where you have trig functions involved, solving for t with trig functions, don't want to do that. I do not want to have t equals the inverse cosine of some crap and then have to take that and plug it into the sine curve. It's going to be a mess. So there are some tricks that I will show you in order to solve this one. This one is particular because you have trig functions involved in there. First thing you do is take the x equation, solve it for cosine of t. So yeah, divide both sides by a. X over a equals the cosine of t. Do the same thing for the sine of t. Divide both sides by a, you get y over a equals the sine of t. And I know what some of you are thinking because I'm really smart. I know what kids think. Sometimes. Other times I'm like, what were they thinking? Just, okay. Pythagorean identity. Sine squared t plus cosine squared t is equal to 1. Pythagorean identity. Sine squared plus cosine squared equals 1. Replace sine with y over a. Replace cosine with with x over a. So that means I have y over a squared plus x over a squared is equal to 1. Square it out. Y squared over a squared plus x squared over a squared is equal to 1. Now, I know that you think, what does this look like? Looks like an ellipse, except for there's one major difference. There's no b, they're just a squared. They're the same number. Multiply it through by a squared. Yeah, so what is this? It's a circle with a radius of a. So what does the graph look like? It's a circle. With radius a.
That's how you answer that?
Yeah, well, that's how you answer this. What does the graph look like? It looks like a circle with a radius of a. How does it change if a is greater than 0? A is a positive value. And t goes from 0 to pi. T is not infinite. Because what's going on here with this one, remember our interval for t on here? Our interval was everything. So as t changes, what's happening is x is this value of t, y is that value of t. This parametric equation, what's happening here is t goes from negative infinity, it just keeps going around and around and around like that. If, however, I limit my inputs, and it's hard to tell from here, but if you look at the original equations, so if I start out at 0, what is the sine of 0? The sine of 0 is 0. The sine of a very small angle is the same as the angle. The sine of 0 is 0. What is the cosine of 0? It's 1. So I start out here. Where does it begin? It begins here at A. As it progresses through to pi, I put in my values for sine and cosine for pi into the original problem. That's all I get. I get a semicircle. It has to be able to go all the way around, right? What does pi give us? Pi only gets us halfway there because it goes from 0. It goes from the point 1, 0 to the point 0, 1 to the point negative 1, 0 at pi. I don't get the bottom half of the curve, do I? I don't get the sine or cosine values that would give me the bottom half of the curve. So if I go from 0 to pi, I only have the top half of the circle. I need to keep going farther to get all the way around. So the t parameter dictates how far around the circle I go, how much I go. Top one's a negative infinity to infinity, so it covers every possible cosine and sine value. So I get the full circle. This one only goes halfway, so I only get a semicircle. Okay? Questions? All right. So those of you in physics might appreciate this one a little bit more than those not yet in physics. You should take physics. Physics is probably one of the best sciences you can take because it explains the physical world, how things move and act around you. Chemistry is good too. So is biology because you ought to understand everything about your body and every living thing. Biology teaches you important things about that.
So is
Physiology. Biology I count as human physiology along those lines, but you should know how the human body works. You should know how your body works. You should know how other people's bodies work. If you have a partner that is not the same sex as you, you should know how their body works too, because you should understand if something goes wrong, what you can do to support them and help them. Makes sense. That's all that has to do with understanding what your partner's going through. Okay. Yes, that's on tape. Okay, so in calculus, it can be shown that the parametric equations of the path of a projectile fired at an angle theta from the horizontal with initial velocity v of 0 and from a height h above the horizontal r. There's the x-coordinate, there's the y-coordinate. Two equations based upon time. One describes the horizontal movement of the object, one describes the vertical movement of the object. So the object, the idea is, we've got an object fired like that. We have one equation that describes what's going along the horizontal. We have another equation that describes what's happening to the vertical. Two separate equations to describe this path. One is strictly horizontal, one is strictly vertical. That's a parametric equation. So I can discuss the horizontal here without regards to the vertical. I can discuss the vertical without regards to the horizontal. Or I can combine the two of them together if necessary if I want to describe the two of them. If I wish to do this in a three-dimensional form, you can just add a third dimension to it and you can have directions and otherwise. Think about a golf ball. The assumption I'm making here is that we're just talking a straight and true path, right? But think about what really happens to the golf ball. You can have one that slices, or you can have one that hooks, or you can have one that slices. The difference between the slice and the hook is which way it curves. But if you have a curve to it, not just a straight going away, but let's say the ball curved due to wind or due to rotation of the ball or something like that, you want to add another dimension. You add z based upon time as well. You can do that and describe it three-dimensionally. Okay. Now, we're not going to do that here because we're lazy. Okay, t is time and g is the gravitational constant. What is the gravitational constant? 9.8 what? 9.8 meters per second squared. However, read the problem. Meters per second squared and feet. We've got a unit compatibility issue. Do you really want to change feet to meters? Does anybody know what the gravitational constant is in terms of feet? Oh. And I don't blame you because you guys don't use it in school anymore. 32 feet per second squared. Yeah, it's actually a much easier number to work with because there's no decimals involved. Gravity measured in feet is 32 feet per second. 9.8 meters, 32 feet per second. Part of the reason it's ingrained in my head is because my dad learned it all at feet when he was a kid. He would spout it off to me growing up because, you know, we're geeky science kind of family. Although my mom was a librarian, so I had the other end of the spectrum too. But yeah, 32 feet per second squared. Okay. So, our initial velocity of 150 feet per second. So this would be v sub 0. 0 is initial. That's where you start. V sub 0. 30 degrees to the horizontal. This is our theta. And yes, your calculators need to be in degrees for today's work. Okay. Yeah. So the first question is to find the parametric equations that describe the ball as a function of t. In other words, plug in theta, plug in the initial velocity, and use the gravitational constant in the two equations to get x something t, y something t. Get rid of the other stuff. So plug in those values is what we need to do first. So for x equals the initial velocity of 150 feet per second times the cosine of our angle, which is 30 degrees, times time. Now, I do not have the decimal version of that on my notes, but the cosine of 30 degrees is root 3 over 2. So when you simplify it down, you get 75 root 3 times t. That is my x1. If you have the decimal version of that, that's fine. On the test, I will have those. I just don't have that in my notes for this one. So there's the x1 based upon time. So if I want to talk about anything horizontal, that's my description of anything that's going on horizontally. At any time period, where is it along the ground? If I were to go to a certain place at like 1 second, go step over this first distance here, the ball would be directly over my head. That would be the horizontal. After like 5 seconds, I'd walk out however x told me 5 was, and the ball would be directly over my head. Or hitting me in the head, depending upon what's going on at that time. But it would be there. It would be where it was horizontally, not vertically. Okay. How high up off the ground it is determined by the y. So I have y equals negative 1/2 times 32 feet per second squared, t squared, plus the initial velocity, 150 times the sine of 30 degrees times t, plus h. H is my initial height. Where is the ball when I begin?
0.
0. It's on the ground. I'm not standing on the edge of the cliff. I'm not hitting golf balls off the deck of a cruise ship. I'm standing on the tee, which means it's at ground 0. Well, that didn't sound good. So h is 0, so I can just not put h on there in this particular case. I'm not on a launch pad. I'm not on an elevated tee. I'm right on the ground. Okay. Simplify it out. Y equals negative 16 t squared. That's a very common way to write almost all of them. Acceleration due to gravity, that's what you'll get. The sine of 30 is 1/2. Because if I get root 3 over 2 for the cosine, that means 1/2 is going to be the sine. Half of 150, so I get 7 plus 75 t. So that simplifies nice. So I've got one equation that describes where it is off the ground, one that describes where it is along the ground. Two independent motions. And this is nice for some of the things we're going to do. It makes it easier to work with. Okay, we have one that describes the height, one that describes where it is on the ground. So my first question I have here, how long is the ball in the air? Well, where is it when it's not in the air? On the ground. What is the y value for when it's on the ground? 0. So to do this, we let y equal 0. So that means I get 0 equals negative 16 t squared plus 75 t. Now, you're going to get two values of t. I can take this and simplify this out, and I get 0 equals t times negative 16t plus 75. Right? Factored out. First factor equal to 0. T equals 0. That makes sense, because where does it start? On the ground. So time 0, it's on the ground. That makes sense. When does it hit the ground again? When negative 16t plus 75 is equal to 0, or at time equals 4.6875. So not quite 5 seconds, it's going to hit the ground again. So it's going to be in the air for a little less than 5 seconds. Goes up and lands. In between, it's in the ground, in the air. Okay? Questions so far? This makes sense, right? You understand what's going on? Can you visualize what's happening with the ball, and how we're examining what's going on? Remember, this is a very simplified version of a basic physics problem, okay, which calculus works really good at. Okay. When was the ball at its maximum height? So it starts on the ground and ends on the ground. When's it going to be at the tallest point off the ground? Right halfway in between. We're ignoring wind and all that stuff. So halfway in between. Time equals 4.6875 divided by 2. Halfway across the ground and halfway there is what it's going to be. Because it's half the time it takes to travel in the air, halfway across it's going to be at its maximum. Because it's going to go up, and then gravity's going to kick in and start pulling it back down again.
Are we ever going to be called where you incorporate weight?
No, because we do not possess the math. You do not possess the mathematical abilities to include those equations into the problems.
Wow.
Trust me. No, none of you do. I barely do. I do, but I have to go back and research how to do it.
Oh.
I have done the math. It's been a long time. Yeah, you seriously need some serious stuff to start doing wind speed and air resistance and all that crap into it. And you can get some serious equations going. So our time would be 2.34375. Now I carried that out. I carried it out way more decimal places than you need to. I know. I know. I've told everybody that it's dying. It's dying.
So your eyes are done?
What?
What's done?
Screen. I thought you were talking about the flashing on the screen.
Yeah. You weren't talking about the flash.
I hope nobody in here. So, it says determine the height. Okay, shh. Which equation is going to describe the height? Which equation describes the distance? X is distance, Y would be height. So where do I plug that? I plug it into Y, because Y is how tall. So I take that number, plug it into the Y equation. Y equals negative 16 times 2.34375 squared plus 75 times 2.34375. And its maximum height was 87.89 feet. Yes. Okay, the question asked, when is it highest off the ground, right? When is it going to be highest off the ground? Halfway between when it started, when it was on the ground and when it was on the ground again. Halfway between. So you take how long it took to land again and divide that by 2 and you get how long halfway in here. Now, how far did the ball travel? Which equation deals with that? X. So here's what you do. Plug in the time that it was in the air from when it hit the ground, when it hit the ground again, into the horizontal equation. X equals 75 root 3 times 4.6875. And the ball went about 608.9 feet. About 200 yards. little over 200 yards. Okay. Parametric equations are really good at describing motion. Parametric, this is really what the best thing about parametric equations are, describing motion of an object. Because you can break it down into, ooh, I'm only going to talk about the horizontal, I'm only going to talk about the vertical. And you can do with them independently, not together at the same time, and it works really well for that. Okay, questions?